Hey everyone, this is Muhammad Nadeem and welcome to my YouTube channel. Today we will demonstrate about Faraday Law of electromagnetic induction, and in this same video we will derive the expression for Faraday Law of electromagnetic induction. So for the demonstration we have these three main operators. So the first one is this permanent magnet, and here this magnet will produce the magnetic field around itself, and that magnetic field will be extended up to some region. I mean that if I bring the test magnet to that region, the force will exert on that magnet, and it will be attracted toward this magnet. So here, around this magnet there will be some region in which the effect of this magnet will be present, and that region is called the magnetic field. And if we are if we come near to this magnet, the magnetic field lines will be close together, and if we move away, the magnetic field lines will be away from each other. So I mean that the magnetic field strength will be more near to this permanent magnet, and that magnetic field strength will be gradually decreasing if we increase the distance between the two magnets. Okay, so this is that permanent magnet, and here these are the coils, and this is the first coil. So this coil is made by the copper illuminated wire, and here this copper illuminated wire is about 0.2 in diameter, and here is about 110 number of turns present in this coil. And similarly we have this same this coil which is made by the same copper illuminated wire, and the diameter of that copper illuminated wire about 0.2 in diameter, and here in this other coil the number of turns is about 110 in this coil. And these two coils we connected with the we connected by this connection. So this is the first coil, okay, and this is the second coil, and we connect these two coils with each other, and the other terminals of this first coil we will connect with the one probe of this galvanometer. Here this galvanometer is a device which is used for the detection of the small current. So the one probe of this galvanometer we will connect with the one coil, and the other probe of the galvanometer we will connect it with the other wire of this coil. I connect that, okay, and these two coils are also so here these two coils are connected with each other, and similarly the other wire of this coil is connected with this probe of the galvanometer, and the second wire of this uh, coil is connected with the second probe of this galvanometer. Okay, so by bringing this magnet near or away to this coil, the EMF will be induced in this coil, and that EMF will be shown by this apparatus. So here I'm going to change the magnetic flux through this coil, and see here it show the deflection. It shows the deflection. So this deflection, so if we bring this magnet towards this coil, the deflection will be in one side, and if we bring this magnet away from this coil, the deflection will be on the other side. So now I going to bring this magnet toward this coil, and you have to focus on this needle. Okay, in this case if I bring this magnet to this coil, this galvanometer show deflection on this side. And if I bring this permanent magnet away from this coil, the deflection will be on the other side. So I'm going to bring this away. You have to focus here. Now it has shown the deflection on the other side. And again, by bringing the magnet near to this coil, the deflection in this side. By bringing it away, the deflection on this side. Okay. So here, in this way, the EMF is changing with time, and this properties is present in the AC current. This property is present in the AC current. The AC current change its polarity with time. In this country or in other countries, the frequency of alternating current is about 50 hertz. It means that 50 times it will change its polarity. Okay, so this produce the alternating current because it change its polarity with time. Okay, so here this EMF induced due to the change in magnetic flux. So as we discuss in the start of this video, this magnet will have some magnetic field, and the magnetic field lines are more closer to each other near to this magnet, and that closeness will be that magnetic field line will be move away if we go away from this magnet. Okay, so therefore, on the other word, we can say that the magnetic flux will be more here near to this magnet, and that magnetic flux will be gradually decreasing if we increase the distance between the two magnets. Okay, so here if I bring this magnet near to this coil, so if it is present at more distance, the magnetic field line will be less fast. A less number of magnetic field line will be passed through uh, this coil. And if I bring this near to this coil, the magnetic field lines will be more passed through this coil. And if I bring it near to this coil, okay, the large number of magnetic field line will be passed. So by changing the magnetic flux, the EMF will be induced here. Okay, by changing the magnetic flux, the EMF will be induced. So according to Faraday law of electromagnetic induction, the change in magnetic flux will induce EMF, okay, in the conductor. So here is that demonstration. So if I increase the number of turns, mean if I double the number of turns by putting one coil on the other, on the top of the other, so here the number of the turns has increased. Okay, so now if I bring this magnet away or near to this coil, this deflection will be more, because here the length of the conductor has increased by increasing the number of turns. So focus here. If I change the magnetic flux, now if I bring the change the magnetic flux, the EMF will be induced, and now the EMF will be more. Okay, so now the deflection is more because here I increase the number of turns. So if we increase the number of turns, the EMF induced will be more. Okay, so here we conclude that the if we increase the number of turns, which is denoted by this N, the EMF, the induced EMF will be more. So the induced EMF is directly proportional to the number of turns. And now, so if I bring this magnet instantly to this coil, the EMF will be more. And similarly, if I bring this magnet slowly toward this that coil, the EMF will be less. Okay, so here the EMF will be less, and if I bring this instantly, the EMF will be more. Okay, so the other factor here is the change in magnetic flux. So if we change the magnetic flux slowly, okay, then the EMF will be less. And if we change the magnetic flux, so if we change the magnetic flux instantly, the EMF will be more. Okay, EMF will be more. And by changing the magnetic flux slowly, the EMF will be less. By changing the magnetic flux instantly, the EMF will be more. So here this induced EMF also depend upon the change in magnetic flux in time delta. So this induced EMF is directly proportional to the change in magnetic flux with time t. So the EMF is directly proportional to n del phi b divided by del t. And instead of this proportionality sign, we will put the equality sign and the constant. So this induced EMF is equal to n constant and n del phi b divided by del t. And instead of this constant, we will put k. So k n del phi or b divided by del t. So if k is equal to 1, then it will be equal to n del phi divided by del t. This is the final equation. So here in this final equation, we will put this negative sign. So this negative sign is explained by the Lenz's law. So we will discuss that in the next video. According to the Lenz law, the EMF induced is always oppose the change in magnetic flux in time delta. Okay, so we will discuss that later in the upcoming video.